All right, so this was the setup last time. I think we had sort of a category with enough injectives, a left exact functor, something like this. So we had F was a left exact functor between abelian categories A and B. We had the quotient functors to the derived categories of A and the derived category of B. Here, this is just F applied to these complexes. But we also had I think I denoted this like this. So these are the homotopy categories of complexes that consisted of injective objects inside of A. So again, I can take these guys bounded, and this was an equivalence of categories. So the key was that this was an equivalence of categories, and this is inside of this. So if I grab an object here, some complex A, I can find an object here. There was some complex I, an isomorphism between this complex and this complex in this category. So in this category, such a morphism would be something like a map from a larger guy to this I, where I have a quasi-isomorphism, and then I map this way. But any morphism like this in this category was the same as an actual morphism of complexes in this category. That was a key point. That whenever I have this situation where the target is a complex of injectives, then there actually exists such a map of complexes up to homotopy. And then just the image of that guy across this functor, which is just F of that, is an object in this category that is well defined, that only depends on this A up to isomorphism in this category. Namely, if I pick another B and a quasi-isomorphism between them, or even stronger, if I pick an actual isomorphism in this category, that means if I have a quasi-isomorphism like this and a map to B, then I would get the same object here. In other words, I will find this guy, but up to isomorphism in this category. Well, of course, if I had the same thing with enough projectives, so if I have a right exact functor G is, say, between A and B. Well, actually, let's keep using F because it was using G as an adjoint to F. And enough projectives, then same thing. It's just that now I'll take complexes bounded above. So the functor from the homotopy category of complexes in A bounded above to the homotopy category of complexes in B bounded above, which is applying F to each one of these objects, is an exact functor of triangulated categories. And I can use now the of projective objects in A. And this is an equivalence of categories and the same thing as before. And I can just apply to a complex A here. I find a projective object and a quasi-isomorphism to A, and I just apply that functor F to that projective object. And that's just the same definition that we had before. All right. Okay, so here's an observation. Let's look at take a category. We have our A. I'll look at the situation there where f is the functor hom A dot. So this is in my category A, and this is a functor that goes from A to abelian groups. Actually, since my categories were k-linear, this is a functor to k vector spaces, but it doesn't matter. So it's a covariant functor, takes a B, and it sends me to hom AB. And of course, the derived functor is going to be our hom. And I compute this by, if you give me some B in A, again, by the same argument that we did before, we construct a quasi-isomorphism between this B and a complex I, and this is a quasi-isomorphism. We obtain this hom A I, which is a complex, and I take the homology of that complex in degree n, and this is what I called before X and AB. But if I don't take this homology, I have this derived functor R hom. So here, this functor that we constructed this way is the derived functor RF. So I have this R hom A dot, which is the corresponding functor between the derived categories, D plus A to D plus of abelian groups. And what I could do is just take our hom of A, B. So now this is now an object of this category, and objects in this category were complexes. I can take the homology of that. So this, by definition, is this is just a name for that homology. This is the right derived functor of hom. AB, and we know that this is just X and AB. But something interesting happens, which is that since I have this equivalence of categories here, I can compute this functor R hom by replacing this B by I. So since I have that B is isomorphic to I, is an actual isomorphism in D plus A, then R hom AB as an object in this category is the same as R hom AI. Well, not equal, isomorphic. So that's in this category. But on the other hand, these morphisms, these R hom here, are actual morphisms in the derived category. So let me state it, and let's compute this. So let's look at hom in the derived category, D plus A, between A. This is an object of A, which I am viewing inside of D plus A as complexes that have homology only in degree 0. And now let's look at I. Let's see where I want to do the shifting. let's take this shifted by n. So this here is a complex of injectives. I just grab the complex I and shift everything. It's still a complex built out of injectives. And I know that HOMs in the derived categories, where the target is a complex built out of injectives, is the same thing as HOMs of actual complexes in the homotopy category between A and that complex, I shifted by N. Now, what is such a morphism now of complexes? So I have my A, which sits in degree 0. And now I have this complex of injectives, which is shifted by n. So that means that the degree 0 piece of that guy is in. The degree 1 piece is in plus 1. Here I have the differential of this complex is I in degree n. Perhaps there's a shift, there's a sign of minus 1 to the n that I don't care now. Here I have in minus 1. The differential again, so there's a minus 1 to the n in the differential, but that's irrelevant. Here the differential is of the complex I, and a map of complexes is just a map here, and of course, everywhere else it has to be the 0 map. But the fact that this is a map of complexes, it means that this map here, let me call this guy phi, needs to land in the kernel of this differential. Because for this guy to commute, I need to send this phi of A, dn of that, to the same thing as this, which is 0. And now from this side, it doesn't matter, it's going to commute, of course. So the only condition here is that phi of A is inside of the kernel of d and I. So a map, a morphism here, is the same thing as a morphism here. And a map of complexes is a map such that, oh, I'm sorry about that, is a map such that the image of A is in the kernel of the differential. Just turn this off. On the other hand, these aren't really just maps of complexes. These were equivalence classes of map of complexes. Right? So if I had written here HOM in coaching complexes in A, that would be it. It's just any map like this is a map of complexes, and that's it. But the problem is that here I'm identifying two maps when they are homotopically equivalent. So the question is, when is such a map of complexes homotopically trivial? Okay. And then being homotopically trivial, it means that I can actually lift this here. That's going to be my splitting, because all of the other ones are going to have to be 0. The only possible homotopy is going to come by a map from A to in minus 1, making such that, now let me call this guy f, such that f and d plus 0 is equal to phi. So this guy is homotopically trivial whenever phi of A is equal to dn minus 1 on the complex I of f of A. In particular, it means that this phi is actually in the image. So what we get from here is that the homology in degree n, or in other words, that this HOM here in this homotopy category is the homology in degree n of this complex. In other words, we have Rn HOM A B, which is X n A B. This is equal to HOM in the derived category A I shifted by n, but this, well, this here is equal to hom in the derived category of A, B shifted by N. This is just simply because I and B are equivalent, are isomorphic in the derived category. So I get this equality, which is an interesting equality, that X groups between, say, just two modules is the same thing as shift 1 by N and look at actual honest homomorphisms in the derived category between these two complexes. All right, so I would want to do the same for complexes instead of just objects. Here A and B were objects in this abelian category. So what happens if I want to replace this by complexes of objects? So the problem here is that I do not have defined this. Oops. So if I give you cochain complexes, I haven't defined this. Because I haven't told you what, so I only defined this right derived functor to a left exact functor between the abelian categories, or to an exact functor between the homotopy categories, but I haven't defined you that exact functor between the homotopy categories. So in order to do that, in order to deal with this thing, or a slightly more general setup, let's notice something. So the only thing that we needed in the construction here was this category and an equivalence of categories here. This was a strong thing. And the hard part to prove about injectives here it's the only thing that took us some time, is the fact that if I had any roof between an object, between a complex and a complex built out of injectives, it's actually realized by a map well-defined up to homotopy. That was the key part that gave us this equivalence of categories. Once I have this, then grab any object, pick the corresponding object here, realizing it, and apply your functor, and that's it. Everything was trivial after you give me this equivalence of categories here. Now, how was that we proved this statement here? We only needed the following out of the complexes of injectives. So the only thing we used is that we had this I. Let me call this now, I'll say FA. Let's do this in the most general case of the, really FA is a bad name. Let me say it like this. Let's say KA inside of the homotopy category of A. So these are going to be complexes with the following properties. So we want first the fact that if I apply F to an acyclic complex, then I get an acyclic complex. If I have some object, some complex in here, acyclic, then F of this is acyclic. So this is in K plus B. Now again, F only needs to be defined in the homotopy categories. So here F is a functor between K plus A and K plus B. It doesn't need to be coming from a functor from A to B. Okay? So it needs to be an exact functor of triangulated categories between the homotopy categories, but it doesn't really need to be a functor defined naively from a functor of the abelian categories. Now, of course, when I take Ka to be complexes of injectives in A, this satisfies this. For any left exact functor of the additive categories, this was satisfied. And B, for any A in K plus A, there exists an I in Ka such that, and an isomorphism, and a quasi-isomorphism between A and I. Which again, it took us some time to prove this, but it wasn't so hard. So whenever we have enough injectives in the category A, this category does satisfy this property. For any complex, we constructed a resolution by, or a quasi-isomorphism by a complex of injectives. Okay, so if I have this situation, a functor between the homotopy categories and a subcategory, a subtriangulated categories of complexes satisfying these two properties, I'll say that Ka is adapted. To F. And what happens is that if you're in this situation, then you can just use that instead of the category of injectives here. Just replace this by Ka, and whenever you have an object in your derived category, you pick the one given by 2, which is quasi-isomorphic, as an object inside of here. You apply your functor, and you get everything well-defined. The only key part was this, and this is satisfied by 2 as well. That you can just, instead of using I, you can use this Ka. And of course, reverse arrows to get the corresponding statement about projectives. Let's let me specialize that situation where the case where F actually comes from a functor, a left exact functors between the abelian categories. Then now I'll define Fa to be inside of A such that, well, such that if I look at complexes whose objects are inside of Fa, so this is inside of the full homotopy category of complexes of objects in A, satisfying the same two properties. Namely, one, whenever I apply F to such a complex, it's a cyclic if I is a cyclic. Same condition. It's just now my complexes are of objects with a particular property inside of the abelian category. And 2, every A, which is an object of A, admits a resolution in F of A. Resolution with I dot, a complex in F of A. So that's a particular case of what's 2. In that case of what is written there. There I required my F to be defined only at the level of complexes. Here my F is defined at the level of the abelian categories. And then I don't need to require to have a quasi-isomorphism from a complex. I only need to require to have a quasi-isomorphism from objects in my abelian categories. Oh, this is here. So once I have this, then I can just produce for any, the same way that we did it for injectives, for any complex in K plus A, we can construct a quasi-isomorphism within an object like that. Okay? So this is a quasi-isomorphism. And you do this exactly the same way that we did before. You grab A0, let's say that this is bounded below, because this is in K plus. Let's say that it's bounded below at 0, or you start with the first guy, you find your resolution, and then you do the same trick that we did before. So we had this I0, and then some A1, and you use this to construct some I1, some sort of Cartesian diagram, and then we needed to mod out by something. But you just construct the same way this isomorphism. So this category here, this class of objects FA is adapted to F in the sense that this K plus of FA is adapted in that definition there. Okay, so injective objects are adapted to any injectives. So namely IA equal to FA is adapted for any left exact functor. So in particular, if you have your FA containing all injectives, whatever FA is going to satisfy this condition, or the second condition there. Right? So take any FA, as long as it contains all injectives in your category, and you have enough injectives in your category, then you're going to have this condition, because you can just take an injective resolution. And that's by definition is going to be a resolution by objects in K of plus of FA. But you're not going to get this for free. So you need to get this for free. You need to require this. So in particular, if you take FA to be a category that contains all injectives, then it's going to be adapted if and only if the functor F sends a cyclics by a cyclics. So if your category A contains enough injective, has enough injectives, and FA contains all injectives, then FA is adapted whenever I is a cyclic. And then you can use this category instead of just injectives to compute the derived function. Same argument as before. If you do the same for right exact functors, we already have an example of that. So similarly, for right exact functor, and enough projectives. Just that actually, so we have an example of this situation where we have a category with enough projectives, say modules over a ring has enough projectives, and we have a functor which is right exact, and we can compute the left derived functor of that functor by using a cyclic object. So we have this example where our functor F is tensor product by a module M over a ring R. We have enough projectives, so we can compute this guy by taking projective resolution of this argument, or we can compute this by taking resolutions by flat objects, flat modules, which is more than just projectives. In particular, these contained projectives And the point was that if I had a complex of flat modules that is acyclic, then tensoring by M is still acyclic. So that's why we could compute Tor groups, which are the right derived functors, the left derived functors of this functor. We can compute it by using acyclic, by using flat modules, flat resolutions instead of just projective resolutions. Okay, so let's apply that to this situation, which is one of them. So I want to use both flat resolutions and also this situation of computing the derived functor to a functor that is only defined in complexes and not in objects. Okay? So I want to define this. So now notice that if you give me A and B in K of A, well, let's pick this in K plus of A, then hom in K plus of A between A and B was a quotient of hom of hom chains A, B. In particular, this was a collection of maps from AN to BN, commuting with differentials. Okay, but there's an extra hom, which is an internal hom to this category, because this category also has an internal hom. So I can look at hom bar in chain complexes between A and B. And this is a direct sum or a direct product. It depends on which category you are. But these are maps. These are going to be linear maps. These are going to be collections of maps between A. Well, let me tell you what it is. So this is a complex in particular. So since this is a complex, let's call this guy H, just as a shorthand. What is the nth, the degree n piece of that complex? This is going to be hom in the category A between A and B, AK and Bn plus K, and take the sum of those. Overall, K. Sorry? Oh, shit. Yeah, you're right. Let's change the name. Pick a name. Okay. I need a name. Let's use this. No, that's also going to look like homology. Well, for lack of thing, I'm going to call this H. How about this? AB. Let's just keep the whole full hom, and that's it. The degree n piece of this, of hom AB internal in degree n, is this. So I'm just giving you now, this is an object in the category A. Okay, so this is an object in the category A for every n. So now I need to tell you what the differential is. So I need to give you a map to hom internal A, B in degree n plus 1, which is a sum over K now from AK to B n plus 1 plus K. Okay, so there's two differentials that I can take here. I can map from AK. Well, let's pick a phi here in this component, and I need to tell you what is this the image of phi here. Okay, so phi is a map from AK to BK plus n. It increases degree by n. So I have my phi that goes from AK to bk plus n. And I can do two things. I can apply d on the complex b here, and I will land in bk plus n plus 1. Or I can apply d in the complex a and land in ak plus 1, and then apply phi to land in bk plus n plus 1. So that's going to be my d phi. So d phi of A is going to be a linear combination of these two things. It's going to be either phi of A and then apply dB, here it's going to be a sign choice. I'm going to make this one because I'm not going to care about signs. But I will use phi of G of A. Here, D is in the complex A. You might want to choose add a sign minus 1 to the n, and probably that's the usual one. So I'll probably add that sign. So I'll probably add here minus 1 to the n. So in particular, a phi in Hom 0, which is in the kernel of this, is a map of complexes. Okay? That's the whole thing. So exercise, check that this with this is a complex. Exercise. It's just trivial. It's just d squared phi is equal to 0. So it is a complex. And the second is that the homology of that complex in degree 0 is my home. Okay. Okay, so now I have a functor. Well, for chains, in Hom chains, and then you can do the same for this. So define the same way a functor, this internal Hom in the homotopy category. So this is going to be a direct sum of maps like this. So maps that increase the degree by n, and the differential is defined by the same formula. Okay, so the statement is that the complex, so this homotopy category of injective objects in A, if A has enough injectives, is adapted for that Hom. To that functor. And the proof of this is exactly the same that we already did. So the only thing I need to check is that, well, I need to check 1 and 2. That if I have an acyclic object, then applying our Hom is still acyclic. And this is absolutely trivial. It's exactly the same thing that we did before. 2, of course, holds, because we already know that for any complex, we can find a quasi-isomorphism to a complex that is built out of injectives. So the only thing that we needed to check is that this thing sends a cyclic to acyclics. Okay. And now once you have that, then you get exactly the same thing of X groups that we've computed at the beginning. I'm not going to have time to finish. So out of a corollary of this is that xn, now I can define this, xn a b as the n homology of that complex. So I take the hom a b the a. This, by definition, is the degree n homology of the derived functor to that hom d plus a ab. So that's just the definition of this Rn hom. And on the other hand, this is the same thing as an honest hom in d plus a between a and b shifted by n. So I can compute n group. Oops, here is b. Shifted by. I can compute x groups by just homs in the derived category. And that's a general statement. Well, let me just write this in a different way. So what we are finding is that we have this functor from observation, claim, well, observation. So this functor here is well defined. So hom R hom d plus a dot, like this. This guy is well defined from d plus a to d plus a billion groups. But it doesn't really need A to be bounded. As long as this guy is bounded, we're fine. We get a bounded hom. So remember, these d plus are bounded below, and this thing here thinks that increase degree by k. Let's say that this is bounded below at 0. So this R hom is going to be bounded below because it doesn't matter how negative this A is, going to have to go to 0 in negative degrees because this object is 0 in negative degrees. So this is well defined regardless of A being bounded or not. Second is that this is functorial in A. In A. Namely, if you have a morphism, so let's say, suppose that you have a morphism from A to B, but a morphism in DA so remember, this means some guy like this. Then you get a well-defined map from R hom B to R hom A. And it's well defined on DA in the sense that if this is an isomorphism, then this is an isomorphism. Or in other words, if you have a quasi-isomorphism between A and B of complexes, then these two guys are isomorphic. They're isomorphic complexes. They're quasi-isomorphic complexes. So, summing up, what you get is a functor from the derived category of A, not bounded, times the bounded derived category of A, and this is opposite, to the bounded derived category of abelian groups or K vector spaces, where you send A here, B here, to our home, AB. On the other hand, since we can use projectives, well, we can take a projective resolution of this A, and projective resolutions of A in this category, they are injective objects here. So a projective in the opposite category is an injective object here in this category. So that means that, and since injectives are adapted to any functor, then this means that you would get now, by taking projective resolutions of A, something like this. You'll need A to be bounded, and B might not be bounded to our home, AB. Oops, sorry. Our home abelian groups. To the derived category bounded above of abelian groups. And it's the same situation, it's just that now A needs to be bounded above, B doesn't need to be bounded, and you take this R home. But the domain of definition of these two functors is different. So in order to be able to compute this guy, we needed A to be bounded above, so that we actually find a quasi-isomorphism between a projective complex and A, or a complex of projectives and A. Otherwise, we don't even have such quasi-isomorphism. Okay, so in their intersection, namely when A is bounded and B is bounded, you get something that is bounded. You could do something slightly better. You could just take something A bounded above, B bounded below, and you'll get something bounded. But the whole point is that these two things are different functors defined in different places. But if I take A bounded above here, then I will compute something. And if I take B bounded above there, I would compute something. And this thing would agree if both of them are bounded, which is here. Okay. So we have this, which sounds like abstract nonsense. But the fact that this is an honest morphism in a category gives me a ring structure on X groups that wasn't trivial to compute if I did it just by taking X resolutions. So these are honest morphisms, and honest morphisms can be actually composed in a category. So I have a composition. GA is a category, therefore I can compose. Has compositions of morphisms. So let's suppose that you have A, B, and C, which are chain complexes. I'm sorry, co-chain complexes, but I'll just take them to be bounded. Then there exists a natural map between XP, AB, XQ, BC, and X P plus Q AC, which is given as follows. Suppose that you have some object here, So then this guy is hom in the derived category between A and B. I'm not going to write these dots. Shifted by P. This thing here is hom in the derived category, between B and C shifted by Q. And this thing here is hom in the derived category between A and C shifted by P plus Q. So these are all isomorphisms. But now, shifting is an equivalence of categories. So in particular, I have that hom dA is the same thing as hom dA plus between B shifted by P and this complex shifted by P, which is the same thing as C shifted by P plus Q. And now, something here is a map from A to BP. Something here is a map from BP to C shifted by P plus Q. And the composition of these two maps is a map here. So this is just composition of maps. And composition is associative. So you get a ring. Well, not really, but you want to get a ring out of that. And in the sense that X, now P, A, B, X, Q, B, C, X, R, C, D. You can map this to X, P, A, B, and multiply these two to X, Q plus R, B, D. Or you can multiply these two to X, P plus Q, A, C, X, R, C, D, and multiply now these two to X, P plus Q plus R, A, C, A, D, sorry. Or multiply those two here, and this diagram commutes. So in that sense, that composition. And this is just the associativity of the composition. There. But these are groups, so those diagrams commute. This is not, well, yeah. In that sense, that multiplication is associative. Okay. So in particular, you can just take the direct sum of all the X groups between an object and itself, and that's an honest algebra. Now, if I take A, B, C, and D to be just one object, then this is by definition an associativity of that product. This we didn't get for free. We get this for free by this isomorphism, which is just abstract nonsense, instead of like doing this by hand. Computing this multiplication on X groups is not so tricky. Okay, I have a little time, so I want to exploit this thing of the adapted categories. So notice something that comes out of abstract nonsense, which is this, is that suppose I have two functors now. I have some F1, let's say from A to B, and I have some F2, well, let's say F and G, goes from B to C. So therefore, I have the composition of G composed with F from A to C. Well, I would want to say that if these are left exact functors, I can compose them and see if I have a left exact functor and compute the derived functors of each one of those. So let me phrase this in a different way. Let's suppose that I have enough injectives in A and B. Suppose that A and B have enough injectives. And let's take some KA, some category that an A adapted to F. And some KB adapted to G. And let's make the stronger assumption that F sends objects in KA to KB. So the typical situation where you would apply, you would see these conditions is you take KA to be injectives in A. That's adapted to any left exact functor. But now your functor F does not send injectives to injectives. That's very hard to check, typically. You need some sort of exactness condition, and we've checked this, that if F was adjoined to an exact functor, that would happen. But typically, you don't have that condition that you send injectives to injectives. But what you can have is that you send complex of injectives to complex of things that are in this category that is larger than injectives in B. So if you were looking at projectives, the situation would be you may have a functor that sends projectives to flats, but not necessarily projective. So you allow yourself some slack by enlarging the category of injectives in B to be larger, which is this KB. But typically, you will take KA to be just injectives, so as small as you can, because you want to impose this stronger condition on that F sends KA to KB, so you want this guy to be as small as possible. And injectives is good enough. OK, so let's suppose that you are in this situation. Then, well, we have a category that is adapted to this G mod F. So first of all, this KA is adapted to F, so G composed with F. This is obvious, because injectives are inside of KA. That's first. And second, if you have some complex inside of here, that composition there sends it to F of this, which is a complex in KB. And then G of that sends it to, well, G of something in KB. If you started with something acyclic, G of something in KB is acyclic, because KB was adapted to G. So this is adapted to this composition. So what I have is this right derived functor for F, and I have the right derived functor for G, and I can compose them. So this is a functor from the derived category of A to the derived category C. And I also have the composition. It's a functor between these two guys, the same two. And these two are isomorphic functors. This statement is trivial. It's absolutely trivial. It's just the fact that they are defined that took some time to cook up. But once we have this setup, the fact that these two are isomorphic is absolutely trivial. How we compute these two guys? So we have K plus A, K plus B, K plus C. We have inside of here this K of KA. Oh, I think I was calling this KA. So inside of here, I have here the derived category for A. So I have an object here. I find something in this equivalence here, and I apply whatever functor I want. Here I have F. Here I have G. if I want to compute the derived functor of f, I will just stop at f. And I will take f of I. And that is the image of this A by the Rf of A, which is this. If I now have this guy, which is in K of B, well, no, let's compute it for the composition. So if I stop at F composed with G, I will compute, I will do F GF of I, and this is R of GF of A. This is the definition. Just grab here, compose these two functors, map it there. How about here? So if I want to compute here G, so the derived functor, I would want to compute the derived functor of G applied to this object, to f of I. What do I need to do? Well, I need to look at KB, find something that is isomorphic to this f of I inside of here, and then apply G. That's the definition. So I look at KB, which is inside of here. I need something that is isomorphic to this f of I, which is itself Rf of A, and apply G to that. But on the other hand, I already know that f of I is itself in here. That was this condition, that f of Ka is inside of Kb. So this f of I can take it itself here. I can map it here to G of f of I, and then I see it here, and I just computed this. I'm sorry, I just computed this. And I've gotten the same answer as that. Okay. So that's this isomorphism between these two. However, these are complexes. And so both of these things are complexes in D plus of C. And I can compute their homologies. So I have three complexes lying around. I have this complex, Rf of A, which is a complex in dB. I have R G composed with F of A, which is a complex in D plus C. But I also have this thing which is Rg of this complex, Rf of A, which is also a complex here. But I can view it as a complex. I can take the homology of this complex. In other words, what I can do is I can look at the nth homology of this complex. So that's Rn of G composed with F of A. Now this is an object in C. It's the nth homology of that complex. Or I could try to compute RQF of A. This is an object in B. And I can take RPG of that object in B. And this is an object now in C. Yeah, I'm sorry for removing things. So this is in B. And the RPG of that is in C. And I may ask, are these two things equal, or when are they equal? And now the comparison is not so trivial. So how can I compare these two? So I have this isomorphism of functors. But what I'm interested in is computing the homology groups. So I need to find a way of comparing these homologies. So I'm interested in computing this homology, and I know how to compute, for example, these two homologies. So let me start with this, and I'll finish next time. So the statement is that there is a spectral sequence that computes that homology, relates these two homologies. And for that, I need to describe what is a spectral sequence. So I'll start with just a definition. And then hopefully today I'll just give the main example without proving anything, and next time I'll just find that sequence that converges. So a spectral sequence is a lot of data. It's a lot of data. It's the following data. So I will have let's put like this. N, a collection of objects. In your abelian category A. I will have another collection, ER, PQ, which is another collection of objects, and here R is bigger or equal than 1. Here P and Q are integers, and N here is an integer, arbitrary integer. I'll impose condition on boundedness of these things, but for now let's keep N, P, and Q integers. But R is bigger or equal than 1. I want these guys to be complexes. So I want maps like this. PQ, D, and I'm not going to, I should write here DRPQ, that I'm not going to write. It's just going to be D, but it preserves R, and it sends PQ to P plus R, Q minus R plus 1. So it increases the first guy by R, and it decreases the second guy by R minus 1. Okay? And so since I have this, I would require that the composition of two such Ds. So this is the data. Yeah, so I'm defining data. So this is not a. So I'll continue with data in a second. But here's an axiom. So here I'll have the set of axioms. I'll write them here. So the axioms are such that D squares to 0. But D square is, well, this is a map now from E, P, Q, R to D, P plus 2R, Q minus 2R plus 1. So, yeah, plus 2. Okay, so that composition is 0. So that this becomes a complex if I put here a dot and a dot in here. Okay? So this is a complex. And once that I know that because of this axiom that those are complexes, now I want an isomorphism between ER plus 1, PQ, and the homology of this complex. Okay. Namely, the kernel of this D modulo the image of the D that comes from P minus R, Q plus R minus 1. Okay. So this thing is the kernel of that D there. From ERPQ to E P plus R Q minus R plus 1 modulo the image of the D that goes from E P minus R Q plus R minus 1 to EPQ. So this, I require these isomorphisms. This is part of the data. This is not an axiom. Still with part of the data, I want a filtration on this object. So far I have these two completely disconnected objects. This these guys that are labeled by 2 indices P and Q, or 3 if you count this R, and then this E that's labeled by only one guy, this N. So I would find a filtration Fp of En that contains Fp plus 1 of En. So this is a decrease in filtration. And it's like this. So this is decrease in filtration of these ENs. And thus filtration satisfies some conditions. So the conditions is that, well, the union of all these FPs is En. Actually, there's an extra condition. So, yeah, so all of these guys are included in En. So I would want that the union of all of them is the whole of En. I would want that the intersection of all of this Fp, so this over P, is equal to 0. So it's separated filtration. And the final condition is the condition of this spectral sequence converging, is the following. So what happens? Let's draw something before we write that condition. So how does these differentials look like? So let's look at how E1 looks like. So I'm going to draw in this axis P and in this axis Q. And the differential goes from EPQ, something like here. It increases P by 1, and it decreases Q by 0. So the differential goes like this on each one of these. So what I have is just a collection of complexes, which are these horizontal complexes. These are completely unrelated complexes in principle, which are just these horizontal complexes. So here E PQ goes to E P plus 1Q. How does E2 look like? Well, now the situation is slightly different. Let's start putting these guys. So now the differential increases 2 in degree P and decreases 1 in Q. So it goes from here to here. Now I start mixing these different arrows. It goes from here to here. It goes from here to here. It goes from here to here, and so forth. So now the complexes, I have a bunch of diagonal complexes like this. So this is EPQ to E P plus 1 Q minus 1. Oh, P plus 2 Q minus 1. And of course, the next one is going to go P plus 3, and then they go down 2. It's just right off this diagonal. Well, let's get there in a second. What is the condition that I'm going to require? I'm going to require that for each n, this differential vanishes at some point. So let's suppose that I know that the differentials on the second page, so these are called pages of the spectral sequence, all of these E lower R's. This is this like this. And suppose that I know that at some R, all the differentials are 0. So if I know that for example, I know this for a fact if this EPQ is 0, it's bounded below and on the left. Let's suppose that EPQ is only concentrated in the first quadrant. Okay? Since the differential each time goes down in Q by a larger amount, for any n, for any diagonal like P plus Q is equal to n, I know that for R large enough, the differential has to be 0 because it's going to land somewhere. And it actually has to come from 0 because the preimage of the differential is coming from this side. It's coming from the left. So I know that for every bounded P plus Q, I know that the differential is 0 after some R. And once I know that the differential is 0, because of these isomorphisms because of these isomorphisms in the definition, then I know that the homology of a complex is the complex itself. So ER plus 1 is going to have to be isomorphic to ER. And then ER plus 2 is going to have to be isomorphic to this one. So I know that it stops. So these pages become all the same after a certain degree if I know that the differentials are 0 for some reason. And again, what are the conditions that I asked here? Well, I asked that the differential was coming from 0, and the image of the differential was 0. So I'll require that now. So I'll require that for every, let's suppose that for every n, let's see if I want this to depend on n or on p. Okay, I'll require the following. Let's suppose that for every n, there exists an R such, probably an R is 0, an S, which is bigger or equal than 1, such that the differential on E P plus Q R to E S, no, I guess R. No, I'll do this for S. P plus S Q minus S plus 1 is equal to 0. And the differential from EP minus S Q plus S minus 1 to EP plus Q, EPQ S are both 0. If P plus Q is equal to n. So this S depends on n. Might depend on n. So the point is that So if I have this unbounded, but in the first quadrant, then I know that for each diagonal, I will eventually land on 0 and come from 0. But this eventually is going to happen each time for an S, for a larger S, or larger R. If I had this bounded, say, for the first 2 rows, then I don't need to make that claim. Okay, so let's suppose that I have this. Then I know that that axiom star, which is here, implies that ERPQ is isomorphic to ESPQ for every R which is bigger or equal than S. Because the homology of a 0 complex is the complex itself. The homology of a complex with 0 differential is the complex itself. So I'll call this guy, so this is denoted E infinity. notice that there's no choice here because this is part of the data. This isomorphism is part of the data. So I can identify all of these groups by that isomorphism, which is part of the data, and I get that object, which is the C infinity, which is just any of these ERs for R bigger or equal than S. So the last condition is that E infinity, PQ, is isomorphic to F P of E P plus Q. So that's the condition, this relation between these pages and this. So I want to give an example. I have 5 minutes, so I want to say where this comes from. This comes from a filtered complex, but I guess it's easier to see a filtered complex from a bicomplex. So let's start with a bicomplex, and next class I'll start with a filtered complex. So this situation arises oftentimes from having just a filtered complex, and filtrations you get them by, for example, composing two functors, or from starting with a bicomplex. So let's start today with a bicomplex. Let's suppose that I have this complex. It's a bicomplex. Then I will construct a spectral sequence. And the way to construct this spectral sequence is, I mean, this looks like a lot of data. But it's typically what you do is you give me a page, and you define these other ones by this axiom. So you give me ER for some R. It doesn't matter what happened before. And I just define ER plus 1 as this homology. So I just only need to give you some differential that I know it's going to survive. So this is what I'll do now. So this is going to give rise to the EPQs. And the total complex of this bicomplex, which is what I'm interested in computing, is going to give rise to E. N. So that's the object that I want to compute the homology. And this is the object that is going to give me the spectral sequence pages. So E2 of PQ is going to be given by the differential HP in the horizontal direction. Oops. Yeah. Horizontal direction of the differential the homology HQ of the vertical direction of this bicomplex. And En is going to be P plus Q of the total of this complex. Oops, H. P plus Q of the total complex. Okay, so this is this object. So the category A is vector spaces. And I have complexes of vector spaces. This is a complex, and I take the P plus Q homology of that complex. Okay? Remember what was this complex? And here it depended if I took sums or products, and how was the boundedness of this bicomplex. Let's not worry about these kind of things. But this is the sum of P plus, oops. The P plus Q homology of this thing is the sum over P and Q of, let's say if I call this N is equal to that, then this is the sum over P of H. Now, this is stupid. Let's first recall that dot N of this C dot dot is the direct sum over P plus Q is equal to n of CPQ. Therefore, this H, P plus Q, is the kernel of that differential that goes from CPQ to the sum CP plus 1 Q modulo the image. Again, this is P plus Q is equal to n, same thing. And here's P plus Q is equal to n. Modulo the image of CP minus 1 Q. Notice that it doesn't matter if I write this plus 1 here or plus 1 there, because it's a sum into this sum to CPQ. Here P plus Q is equal to n, and here is P plus Q is equal to n. So that's this space En, and this is the kernel of C dot Q into C dot Q plus 1 modulo the image. So this is the vertical differential modulo the image of that differential, Q minus 1, C dot Q. So this is still a complex in the first variable, and the horizontal differential is the differential of that complex, and the homology of that complex is this space, E2. So now I need to tell you what is the differential of this E2. It's already 3. Okay, so I'll finish writing the differential of that E2 in the next case. But the differential of E2 comes from this identification. So the differential D in E2 comes from the differential in the total complex and I'll do this in the next time. I'll write it in the next time. Okay, so at least